Did you know that for centuries, engineers thought that better metal alloys could only come from adding tiny bits of other elements to one or two main ones? They were completely wrong.
Wait, so all those years spent perfecting steel? People thought that was the only asterisk way to make metal stronger? That sounds incredibly short-sighted.
It turns out, mixing a lot of elements in roughly equal measure can create supermaterials with properties nobody expected. Welcome to the world of high-entropy alloys. So what exactly are high-entropy alloys, or HEAs as they're often called? Imagine you're building with Legos. Traditional alloys are like taking a big pile of red bricks and adding just a few blue ones for doors and windows. You have one main building block.
And HEAs are like, you just dump a bunch of different colored bricks together, and suddenly you've got a spaceship that can fly to Mars? How does that even work?
Precisely. HEAs break that mold. Instead of one or two main elements, they typically mix 5 or more different metals in roughly equal proportions. Think of it like a truly diverse cocktail of elements, where no single one dominates. This idea was largely championed by a Taiwanese scientist named Jianwei Ye, who coined the term high-entropy alloys in the early 2000s. He theorized that by maximizing the entropy, the disorder or randomness in the atomic structure, you could stabilize entirely new and incredibly strong materials.
So it's not just about throwing a bunch of stuff together. It's about the asterisk ratio asterisk of those elements that makes it an HEA. But surely people had tried combining lots of metals before Ye came along.
They had, but usually in a more trial-and-error fashion without the underlying theory of entropy to guide them, and often with one dominant element. Ye's insight was that if you have roughly equal amounts of many elements, the atoms arrange themselves in a very stable, often simple, crystalline structure, which gives them their unique properties. For centuries, metallurgy followed a fairly strict playbook. You started with iron or aluminum or copper, and then you'd meticulously add small percentages of other elements like carbon, manganese, or nickel to tweak its strength, ductility, or corrosion resistance.
Right, like how we get all the different types of steel. So the old way was about asterisk improving asterisk an existing dominant metal, not creating something fundamentally new?
Exactly. That's why the emergence of HEAs was such a paradigm shift. It wasn't about enhancing steel, it was about asking, what if we treat asterisk no asterisk element as principal? Research into these multi-component alloys actually began to gain traction in the 1980s, but it really exploded in the 2010s. Scientists realized they could unlock a whole new class of materials with unprecedented strength, toughness, and resistance to extreme conditions.
So who actually made asterisk the first HEA? Or at least the first one that really demonstrated these properties?
While many researchers contributed, Jianwei Ye and his team were pivotal. They systematically explored these systems, leading to the coining of the term and the foundational understanding of why these alloys behave the way they do. Their work showed that by mixing these elements evenly, the atoms arranged themselves in surprisingly simple, stable crystal structures. This chaotic mix often ends up being more ordered and stronger than traditional alloys might predict. Why do these alloys matter today? Because they're not just a scientific curiosity, they are supermaterials. They boast incredibly high strength, fantastic toughness, and can operate at much higher temperatures than conventional alloys.
Higher temperatures, you say? So we're talking about jet engines, nuclear reactors, spacecraft, places where regular metal just melts or falls apart?
Precisely. Think about aerospace propulsion systems, land-based gas turbines, or even heat exchangers in chemical plants. These are all environments where materials are pushed to their absolute limits. HEAs also show superior ductility, meaning they can deform a lot without breaking, which is critical for safety and reliability in engineering. Plus, they often have much better corrosion and oxidation resistance.
So these alloys could make everything from our cars to our power plants safer, more efficient, and last longer? That's a huge deal. Are they already being used widely?
They're still relatively new and often more expensive to produce than traditional alloys due to the complexity of the elements and processing. However, research is accelerating rapidly to bring them into mainstream applications. Many industries are heavily investing in developing and testing HEAs because their potential benefits, from lighter, stronger aircraft components to more durable power generation equipment, are enormous.
So it's not just about making things stronger, but fundamentally changing how we design and build critical infrastructure. So Alex, what's the one thing to remember about high-entropy alloys?
High-entropy alloys prove that sometimes, throwing a whole lot of different ingredients into the mix in equal measure creates the strongest, most resilient materials imaginable. That's Wikipodia, every story on demand. Search your next topic at wikipodia.ai.